Welcome to today's class on vector analysis. Today we discuss the unit binormal vector B and the torsion tau. Now consider R of t, which is the path of a particle in the space. Then at point P, you know the tangent vector t and you know the normal vector n, 1 by kappa dt by ds. Then taking the cross product of n and t, you can see that there exists a vector which is normal to both n and t, which is known as the binormal vector B. So this gives three mutually perpendicular vectors corresponding to each point of the space curve. So we can see a T N B frame on each point of the space curve. So this gives the TNB frame. So TNB frame of mutually orthogonal vectors traveling along the curve R of t. So we define binormal vector. Binormal vector B is defined as B equal to T cross N. So the binormal vector of a curve in space is B equal to T cross N, a unit vector orthogonal to both T and N. Together, T and B define a moving right-handed vector frame that plays a significant role in calculating the paths of the particle moving through the space. It is called the Frenet frame or the TNB frame. So this frame is called the Frenet frame or TNB frame. Now at each point P on the curve R of t, these three vectors T, N and B defines three planes. Plane determined by T and B or generated by T and B is called the rectifying plane. Plane determined by B and N is called the normal plane. And the plane determined by T and N is called the osculating plane. Now you consider the GeoGebra window. You consider the curve R of t to be this curve. Then you can see the T and B frame. So you have, these are the three vectors. This is the tangent vector T and this is the normal vector N and this will be the binormal at P. You can see the movement of T and B frame over this curve in this video. So this is how the TNB frame moves. Here the red vector is the tangent vector, blue vector is the normal vector, green vector is the binormal vector. Now we define torsion. We have B equal to T cross N. By definition of binormal, therefore differentiating with respect to S, we will get dB by ds is a rule of cross products, T cross dN by ds plus dt by ds cross n. We have n equal to 1 by kappa into dt by ds. Therefore, dt by ds cross n, this is equal to dt by ds cross 1 by kappa into dt by ds. So this is 1 by kappa into dt by ds cross dt by ds. So this is equal to 0 since angle between dt by ds and dt by ds is 0. So this is 1 by kappa into modulus of dt by ds into modulus of dt by ds into sine angle between dt by ds and dt by ds. So it is 0 into unit vector orthogonal to dt by ds. So this is equal to sine 0 is 0, so this will be the vector 0. Therefore, from this equation, if you take this as equation 1, therefore from 1 dB by ds equal to t cross dn by ds plus vector 0. So that is dB by ds is t cross dn by ds. So from this we can see that t is orthogonal to dB by ds, or dB by ds is orthogonal to t because a cross b is orthogonal to both a and b. So this implies dB by ds is orthogonal to t. And since b is a unit vector, so it is a vector of constant length, so dB by ds dot b is also 0. So since b is a vector of constant length, we have b dot dB by ds equal to 0. So this implies dB by ds is orthogonal to b. Therefore, dB by ds is orthogonal to both b and t. That is, dB by ds is orthogonal to the plane of b and t. So this implies dB by ds is parallel to n. Therefore, dB by ds equal to minus tau times n, where the scalar tau is called the torsion. The scalar tau is called torsion along the curve. And we have dB by ds equal to minus tau times n implies dB by ds dot n. This is equal to minus tau times n dot n. So this is minus tau into 1. So this is minus tau. Therefore, tau equal to minus dB by ds dot n. So this is the definition for torsion. Thus we have let B is equal to T cross N, then the torsion function of a smooth curve is tau is equal to minus dB by ds dot N. Now we can see some properties of torsion. Unlike the curvature, which is never negative, the torsion may be positive, negative or zero. So curvature is never negative, but torsion may be negative, positive or zero. The curvature kappa is equal to modulus of dt by ds can be thought of as the rate at which the normal plane turns as the point P moves along the path. Similarly, the torsion tau is equal to minus dB by ds dot n is the rate at which the osculating plane turns about t as P moves along the curve. So torsion measures how the curve twists. So if you think of the curve as path of a moving body, then modulus of dt by ds tells how much the path turns to left or right as the object moves along. It is called the curvature of the object's path. The number minus dB by ds dot n tells how much the body's path rotates or twists out of its plane of motion as the object moves along. It is called the torsion of the body's path. For example, suppose that this represents the path of a train. Suppose that P is a train which is climbing up on a curved track. The rate at which the headlight of the train turns from side to side, so left or right, per unit distance is the curvature of the track. So because the headlight is always tangential to the path, so the rate at which the headlight turns from left to right per unit distance is the curvature of the track, and the rate at which the engine tends to twist around the plane formed by T and N. So corresponding to each point, you have a change in the headlight towards left or right. That measure of that is the curvature. And corresponding to each point P on the path, there exists a T and B frame. And consider the plane made by T and N. Then the rate at which the engine tends to twist out of the plane formed by T and N is called the torsion. So that's all for the day. Have a nice day.